Hello, everyone. This is the lecture for section 5.5, alternating series. So over the last couple sections, we've been looking at how to prove a certain series is convergent or divergent, right? In this particular section, we're going to be looking at, in particular, alternating series, okay? And I've already been throwing a bunch of stuff at you guys that sort of get you working up to this already, okay? So first of all, let me start off with the definition of what an alternating series is, okay? So first of all, the definition is anything that looks like this. An alternating series is anything that looks like this. And what pops out, what should sort of tick you off a little bit, right? Or just sort of, the spidey senses should be tingling, right? Is this, that it goes positive, negative, positive, negative. It swaps back and forth. So that's the one on the left, right? It starts with a positive value, right? And it goes negative, positive, negative, positive, negative, right? And the one on the right, it starts with a negative, goes to positive, goes negative, goes positive, goes negative. So in the first one, on the left, it starts with a negative, right? Or sorry, it starts with a positive, right? And then the one on the right, it starts with a negative. That's taken care of by this right here, if you guys take a look at that thing, right? Now, I've already cooked this into some of the examples from the previous sections, right? For right now, right, for this definition, right, in order to make it alternating, in order to make it bounce back and forth between positive and negative and positive and negative, the go-to thing is these two terms right here. It's going to be a -1 to the n plus 1 or a -1 to the n, right? So you get -1 and you square it, cube it, fourth, fifth, sixth, right? The odd ones will produce, the odd powers will produce negatives and the even powers will produce positives. That's what usually works out. This is the thing that we reach for most often, right? But it's not the only one. So like I said, I cooked in some of these representations in your previous sections, right? And we're just going to revisit that as we keep going down, okay? Now, there are two big theorems for this section, okay? One of them is this one right here, the alternating series test, okay? Let me scroll down, there we go. So the alternating series test works on either one of these forms. They're the same ones that I just covered up above, right? Where it starts with a positive or it starts with a negative, right? An alternating series converges if both of these conditions are true. The first one here and the second one here. Okay. The first one essentially states, right? If you take a look at it, bn plus 1 has to be smaller than bn. So this means that your sequence bn, right, has to be decreasing. Right? Your bn has to be decreasing somehow. So this one also, if you want, you can show it with calculus, right? If possible, show it with calculus, right? I'm going to put that here too. And what I mean by show it with calculus is if you can grab the function itself and prove that it is decreasing, so that means take the derivative and make it make sure that it's always going to be a negative derivative. That's great, right? In this section, what I'm going to do is I'm going to show you guys argumentative approaches to proving that something is decreasing. Okay, and then the second one, right, is essentially saying that your sequence, that whatever sequence there is, the bn's, they essentially vanish after a while, right? So the sequence vanishes after a while, that your the bn's, just the limit of them just go to 0 eventually, okay? So long as you prove those two, right, that your sequence is decreasing and your sequence vanishes after a while, right? If you have an alternating series test, that's all you need to prove convergence, okay? Now, The alternating series test, unfortunately, only gives us information about convergence. It's usually used hand in hand with the divergence test from section 5.3 to determine a sum's behavior, right? So this thing is only going to tell you if something's converging or diverging. That is it, right? And lastly, even if we do prove convergence for either one of these alternating series, right? It doesn't tell us anything about the sum. So we can't make the conclusion that it's gonna, it's gonna converge to 5 or 8 or 20 or pi. We have no idea. It doesn't give us that information. It just says it converges. Unfortunately, a fair amount of these series tests that we're doing, right? They only tell you convergence or divergence. They don't tell you what the sum is gonna be. Okay. Okay, so let me go ahead and do some examples. So I've got two examples here, okay? Determine if the series is convergent or divergent. So I know I did both of these at one point in a previous section. This right here, let me start with this one first. That term right there, the very top there, right? That is what's going to give you the positive one, negative one, positive one, negative one, okay? So if you take a look, and to see this, we're going to need the unit circle. So if you don't have it, that's okay. I'm going to draw it really quick. I'm going to do a nice quick review of trig. Here's my unit oval. So what's going to pop up from this thing, right? The yellow is going to be sine, right, of pi over 2, right? Sine of 3 pi over 2. Sine of 5 pi over 2. So if you start plugging in and dot, right? So if you start plugging in n values, right, you'll see that that sine 2n minus 1 pi over 2 is going to get you this list over and over and over again, right? So now, if you remember how trig works out, right, sine of pi over 2, we're looking at this point and the y value, right? Sine of 3 pi over 2 is this point down here. We're looking at the y value. And the y values for both of those is, the first one is positive 1, and the second one is negative 1, right? 5 pi over 2 is coterminal to pi over 2, so we're back at this point up here, so that's positive 1. The next one, sine of 7 pi over 2, bounces down here to negative 1. You guys see what's happening? So sine of pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2, 11 pi over 2, so on and so forth. They bounce back and forth between positive 1 and negative 1, depending on what n it is. So that yellow thing up top is what's giving you the alternating series. It's what's giving you the bouncing up and down. Okay. So then I'm going to rewrite this, right? Not in purple. I'm going to rewrite this way. Whoops, equal. N equal 1 to infinity, right? It's going to be sine of 2n. This is not entirely required. I'm just rewriting it to sort of separate it away. There we go. This is completely valid. That yellow portion is now sort of separated away, right? So now we have whatever is supposed to be the alternating bit, right? The alternating thing that's making it alternate sign, right? So this is sort of equivalent to our negative 1 to the n power. Does that make sense? So that means that this thing right here is my Bn. Okay, so now since I have a alternating series here, right? This thing will converge if two things are true, right? So I'm going to write them up here. Number 1 says that I need this to happen: Bn plus 1, Bn, right? And then the second thing, right? Number 2 states that I need to show that the limit as n goes to infinity of 1, or well, of bn. Let me use the notation from the theorem itself. The limit as n approaches infinity of bn needs to go to 0, right? So let's go ahead and do number 1 first. So this one is sort of pretty sort of obvious. We need to show that this is true. 1 over n has to be bigger, right? Or equal to 1 over n plus 1, right? And for this one, right, you can use you can use the you can use calculus, but what I'm going to do now is I'm going to sort of start. This is something that you should be able to argue at this point, right? That since we have a fraction, right? Let me put that right here, right? Since we have a fraction, we can say this, right? Well, let me start with this. We know that any n plus 1 has to be bigger than or equal to n, right? So that means if we invert them, right, 1 over n plus 1 has to be smaller than 1 over n, right? This is sort of like a bona fide argument for it, right? Another argument that I like to use, right? This is the argument that I sort of run through my head every time, right? Is that we say this, right? For, for bn plus 1, right? The denominator gets bigger. Which means that the fraction, right, gets smaller. What do I mean by this, right? What do I mean by this? It's this, that since this denominator, right, is bigger than this denominator, and the top doesn't change, right? We have that the 1 over n plus 1 is going to be a smaller fraction than the one that came before it. That's it. So we have what we need. So, right, we have 0, bn plus 1. Whoops, wrong b. bn. So we're done. This is checkbox. This is good. We satisfied the first condition. Okay. Second condition says that my limit now needs to go to 0. And that's sort of a gimme, right? So the limit as n goes to infinity of 1 over n, we know that that is 0, right? So that's also a checkbox. That's from Calc 1, right? So that's all I needed. So then therefore, by alternating series test, right? Our original sum, let me write the sum right. Oh my, sum n equal 1 to infinity of sine of 2n minus 1 pi over 2 divided by n converges. Since we satisfied 1 and 2, we know that our thing converged. So there is our answer. So notice how all we needed to really do here, right, is to show those two conditions. And once we showed the two conditions, we were golden. We were good. That's it. That is it. Okay, let's move on to the next example, right? Determine if the series is convergent or divergent, right? Again, this one has, let me bring up the previous one really quick. You can see that thing in yellow that I did in earlier? Cosine of n pi does the exact same thing. So let me explain that one. So I'm going to go ahead and slap down another unit circle here. unit circle oval, unit oval. Okay. So the list that this one's going to produce, right? If you guys notice it, right, is going to be cosine n, cosine of 1 pi, so pi, cosine of 2 pi, cosine of 3 pi, dot, 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 right? Notice how it goes, cosine of pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, right? So now let's look at it on the unit circle. They bounce between these two values right here, right? Cosine of pi is going to be -1. Cosine of 2 pi is going to be +1. 3 pi, -1. +1, -1, +1, -1, and so on and so forth. So in this case, the thing that's that cosine of n pi, right? This is the equivalent to our alternating bit, the -1 to the n power. Oh man. Take your allergy medicine, kids. The pollen is coming. It is coming. Okay, so that is our alternating bit. So all we have to do now is mess with this thing right here, the n squared divided by n squared plus 1. Okay. Again, we just have to solve these two things. We have to prove these two things. So number 1 is prove this, right? It's 0, bn plus 1, bn. Okay. 2 is the limit as n goes to infinity of n, bn, bn. That has to be equal to 0, right? Okay. So we're off to the races, and hopefully what I hope you guys see already is that this thing looks like it's going to be divergent. Okay. So long as one of these two conditions, if either one of these two conditions are not satisfied, right, then we cannot use the alternating series test. We have to use the divergence test from section 5.3. Okay, so let's go ahead and try to prove number 1, and we'll see maybe something goes wrong, maybe something doesn't, right? So let's start off with number 1. Right, so we have to show 0, bn plus 1, bn. Okay. So let's go ahead and try to prove some of this stuff. So we need to show this term right here, this thing right here, right? So in this case, I'm going to go ahead and use the thing that I sort of advised everybody to do here. I'm going to use calculus. Okay, and the way I'm going to do it is this way. So I'm going to use this. F of x is equal, hopefully you guys see it, x squared over x squared plus 1, right? I need to show that this thing is decreasing, right, as x gets bigger. And if I can show that, then we're golden, right? So what I'm going to do, right, is I'm going to take the derivative, so f prime of x. You guys can go ahead and solve it. I've done it already. And that is going to be 2x over x squared plus 1 quantity squared. Okay. Now I want you guys to all realize, right, is that this x value, right, is what we're substituting in for our n value from our series. So if we plug in anything 1 or bigger, right? We plug in anything 1 or bigger, f prime is going to be positive. Since it's positive, it's increasing, not decreasing. So it fails here, right? So here, this condition has failed for the for the alternating series test, right? Okay. So for number 2 now, let's go ahead and move for number 2. Hopefully you guys see the other problem here, right? The limit as n goes to infinity, we need to do it of this thing, right? N squared over n squared plus 1. This is equivalent to the limit as n goes to infinity of 1 over 1 plus 1 over n squared. If you do the calculus right, that thing goes to 0, right? So we have the limit let me just do it. 1 over 1 plus 0, which is 1. Okay, so it fails this condition as well. Okay, since it fails both, we're done. So this series is divergent. Sum n equal 1 to infinity of the cosine of n pi times n squared plus 1, right, is divergent. So that means this number, right, this summation doesn't approach anything in particular. Okay. All right. Those are 2 examples there. Okay. What comes up next now is quick checks. Okay. I'm throwing a couple more things in there for you to sort of try to throw you off, right? Try to identify the alternating bit, try to identify the BN appropriately, right? And see what happens, see what you guys get. Okay. Again, use the alternating series test. The only thing you have to check is the conditions, right? Number 1 and number 2, that the BNs are decreasing and that the BN sequence eventually vanishes. Okay. Try these out. So now moving on, there are a couple of there's a couple of convergences, right, that have some interesting properties once you get to some of the higher math. That is pretty heavy hitting, especially in calculus and the farther studies of calculus, right? And there are some physical applications, some applications in physics that this stuff is used on as well. Okay, so let me get to the definition first. It's called absolute convergence and conditional convergence. Okay, so a series is absolutely convergent, right? A series without the bar. So notice that we are talking about n equal 1 to infinity of a sub n. Okay, that sequence, that series is absolutely convergent, right? If the absolute value of the series also converges. Okay. A series is conditionally convergent, right? If the series without the absolute value converges, but the one with the absolute value diverges. Okay. So the absolute convergence is when the absolute value one converges, right? And the conditional one is when the vanilla one converges, but the absolute value one does not. Okay. There's a fairly deep theorem that comes from this, and that's this one right here. A series that is absolutely convergent is also conditionally convergent. So what that means is this, that if this thing converges, right, the one with the absolute value converges, then the regular one without it must converge as well. Okay, and the idea behind this one is really an easy application of the comparison test and some of the summation arithmetic. So the addition of summations, the subtractions of summations, right? To fill in the specifics of the actual bona fide proof. Okay, altogether, I mean, if you think about it this way, right? If you have 2 things, let me put it down here, right? If you have 2 things, right? if you have the a sub n, just a sub n, right? And then you have the a sub n bar, right? As in the absolute value, right? Then you're always going to have at least this relationship. So remember how the absolute value, right, just turns whatever's in the absolute value bars, it turns it positive, right? Does that make sense? So if this one is just positive, right, and you know that the summation of all of these converge, right, then this one has to also converge. There's the comparison test, right? That simple of a sort of a proof. I'm not gonna do it, at least not here. If you really, really, really want to look at it, it's in the book, okay? All right. Now, how does this work? How do we determine this? So I've got two examples here. Let me actually, so I need to determine whether they absolutely converge, conditionally converge, or they diverge, right? So we're still going to be using the alternating series test here, okay? All right, so to determine whether these conditionally converge, absolutely converge, or diverge, right? I'm going to go ahead and look at both of the, so just keep in mind again, right? This is what's doing the swapping of the negative to positive, negative to positive, negative to positive. So to prove the alternating series test, right? Hopefully you guys see that this is, let me actually rewrite it so you guys can see what I'm talking about. N equal 1 to infinity cosine n pi times 1 over n. Okay, so if I use alternating series test, right, then 1, we know that 1 over n plus 1 is strictly smaller than 1 over n, so this is decreasing, right? We have that much. And 2, we know, this is sort of like a repeat of an example that I did before, the limit as n goes to infinity of 1 over n is equal to 0. So using both of these, right, our sequence converges. Let me do this, converges by alternating series test. We're good there, right? Now, the next one, I'm going to look at this one. The absolute value n equal 1 to infinity of the absolute value, right, of the cosine n pi 1 over n. You guys, hopefully you guys see this. Since it's now absolute value, it doesn't matter if it oscillates back and forth between positive and negative, right? This thing now makes no difference. So I can go ahead and get rid of it. Equal 1 to infinity of 1 over n, right? And this is our harmonic series, right? And this is the thing that we showed long ago, that it diverges, right? Which diverges. So we have this sum n equal 1 to infinity of, let me write it right, cosine of n pi over n, right? This converges by AST. And the sum n equal 1 to infinity of the absolute value, cosine pi, whoops, n pi over n, right, which is equal to the sum n equal 1 to infinity of 1 over n. This diverges, right? So this summation, I'm going to write it down here. Hopefully you guys don't revolt on me. 1 to infinity of cosine n pi over n, right? This is conditionally convergent. Got it? Because the regular summation converged by AST, by the alternating series test. The absolute value diverged because it produced the good old regular harmonic series, right? Since one of them converged, the other diverged, right? We have all that we need to show that our original sequence, our original series, is conditionally convergent. And that is it. That is it. Cool beans, cool beans, cool beans. All right. So now let's do the next one. Okay. So hopefully, I think I've done enough of these, factorial problems. And I think I've given the hint every once in a while. I know nobody's probably introduced the definition of the factorial formally. I've just been doing it in terms of hints, but I'm going to go ahead and do it here for now. So when you have an n factorial, right, with an exclamation, and no joke, that is an exclamation mark. It doesn't mean to shout it out loud. What this means is you are going to multiply all your values up to n. Does that make sense? So this is going to be equal to 1 times 2 times 3 times 4 times ... times n minus 1 times n. Okay, you're multiplying all of these terms all together. Okay, so just as an example, right? 5 factorial, that is 1 times 2 times 3 times 4 times 5. Okay, 3 factorial is 1 times 2 times 3. Okay. All right, so now that you know what a factorial is, okay, now that I've shown you sort of a little bit more formally, right, let's go ahead and use it. Okay, so the first thing I'm going to do is determine if this vanilla version of my sequence or my series is actually convergent. And to do that, since we see that it has the -1 to the n, it's going to be fluttering back and forth between positive and negative, positive and negative. We are going to need to use the alternating series. So that's exactly what we're going to do. My niece is over. Can you hear her playing around with the ball in the back? Okay. So for alternating series tests, right, we need to prove those two conditions. We need to prove one, right, that 1 over, that the bn, well, 0, bn plus 1, bn. We need to prove this, right? Hopefully you guys see that this is. I'm going to go ahead and go through the argument for it, okay? So to prove this statement right here, let me make sure yep, okay. To prove this statement right here, right, we need to show that this is true, right? That I'm going to write it over here on the side. 1 over 2n minus 1 factorial, right, is bigger than or equal to 1 over 2n plus 1 factorial. Okay, to show this, right, it's a little bit of manipulation of the definition for the factorial. Does that make sense? Let me explain how. I'm going to sort of show you guys in general, right? So suppose we had 1 over n factorial, right? Then this is going to be bigger than or equal to, right, 1 over n factorial. Ooh, make the factorial a little bit more. 1 over n factorial times n plus 1. So the argument here, right, is that I am multiplying the bottom by a number that's bigger than 1. So that makes the denominator bigger, which makes my fraction smaller. You guys hopefully see that argument there, right? Okay, that essentially saying like 1/2, right, is going to be bigger than 1/3, which is going to be bigger than 1/4, which is going to be bigger than 1/5, 1/6, and so on and so forth. The same argument can be said. The same argument can be said here, right, with factorial. But notice what happens with this right-hand side, right? N factorial times n plus 1, that is equivalent to n plus 1 factorial. So we proved this. This is done. We're good. This is a good check mark. Number 2. Right, we need to show this. The limit as n goes to infinity of 1 over 2n minus 1 factorial. I'm hoping this is 0, right? Right? And it is. Okay. There is. Let me explain it this way. There is no real decent proof here, other than, right? And this is going to be something that you'll probably see later, right? That 1 over n factorial is going to be smaller than 1 over n squared every time, right? And we know this right here goes to 0, so this one must as well. Ta-da! So we have, right, by these two, right, we have that it is convergent, right? The convergent by alternating series test. We know that it is convergent by alternating series test. So we're good here. Okay. The next one, right? I need to show this, right? Sum n equal 1 to infinity of the absolute value now, right? Of minus 1 to the n over 2n minus 1 factorial. This is now this, right? To infinity of 1 over 2n minus 1 factorial. Since I'm taking the absolute value, right? That oscillating bit, the -1, +1, -1, +1, that just makes no difference anymore, right? I can just eliminate it, okay? Because of the absolute value. So I have to prove what the heck this thing does now, right? And here, right, this is one of the spots where we're going to use a comparison test. This is less than or equal to sum n equal 1 to infinity of 1 over n squared, and this converges. So then therefore, our original sequence, n equal 1 to infinity of -1 to the n over 2n minus 1 factorial, right, is absolutely convergent. It is absolutely convergent. Okay, because the one that's alternating is convergent by alternating series test, right? And the absolute value one is also convergent. So since both are convergent, right, we have something that is absolutely convergent. We are done. Okay. All right. This section was pretty small. It's pretty heavy. I'm not going to lie, right? But that's it. It's only 2 pages. Next things that are up are lecture questions. So I want you guys to try these out. If you guys got problems with them, like always, come to my office hours, come to the tutoring center at the college, or I have my Friday hours all day if you guys need to talk about it there. Okay. Besides that, I am done here. Happy studying.